Okay, so in this video, we will provide a simplified introduction onto how find the surface area of a surface of revolution obtained by revolving a curve about the x-axis. Suppose we have the following curve. Between x equals a and x equals b. Now you can imagine if we revolve this curve all the way around the x-axis, this will generate a surface, what's called a surface of revolution. So let me draw it here. So you can imagine it looks a little bit like some crooked cylinder, right? The cylinder would have straight edges, but now the edges of the outer shell are given by the curve y equals f of x. And of course the center of this surface of revolution is the x-axis. And again, the circular top and bottom is missing. All we have is the shell of this object. And we're asking now very naturally, what is the surface area of this surface of revolution? Well, as always, we will consider a small portion of the surface. We will find the area of this small portion, and then by summing up the area of all the little portions, we will obtain the entire surface area of this surface of revolution. So here I'll exaggerate the picture. So we want to consider a small interval between a and b, and we will, instead of taking the exact curve, we will take a line segment connecting the two endpoints of our interval. Suppose here I'll exaggerate. Suppose we take the given line segment. If I draw down the perpendiculars, then I can imagine this being a very, very short interval, and this is the line segment connecting both points on the curve at the two endpoints. And now, you can imagine that as we let this interval shrink to 0, the line segment will become closer and closer to the actual curve. And so instead of now revolving the portion of the curve, we will revolve the corresponding short line segment, and we'll have a slightly simpler surface of revolution. And this, of course, we think of it as an infinitesimal surface as we will let the width of the interval shrink to 0. So let me draw it here, and again I'll magnify the picture. So what we have in a sense is some type of crooked cylinder, right? If this line segment was perfectly horizontal, then we would revolve the rectangle about the x-axis and obtain a perfect cylinder without, again, the top and the bottom. Now we have a slightly slanted line segment, so we get a slightly slanted, crooked cylinder. But you can imagine that as we let the interval shrink to 0, this will become closer and closer to an actual cylinder. And again, the x-axis goes through this infinitesimal surface of revolution. And now let's look at the key measurements. First, the length of this segment will be approximately the height of this crooked cylinder. Of course, the length of this segment approximates the length of this arc of the curve. And so, of course, we denote this, if you remember our discussion, of arc length, this is ds, the length of an infinitesimal line segment connecting 2 points on the curve, and in the limit, as the interval shrinks to 0, the length of this segment will approach the length of the arc of the curve. So this is approximately the height of this crooked cylinder, and we now need the radius, but if you look approximately, the radius is the distance from the axis of revolution, the x-axis, to this little line segment. Well, again, you can see that depending on which point you choose inside of the interval, you'll get a different distance. The idea, again, is to use an approximation. As the width of the interval shrinks to 0, the difference between different radii will shrink to 0. So we can think of, if this is an infinitesimal interval, take an arbitrary point x in it, and an approximate radius will be the value of the function at this point, therefore f of x. And again, as the interval shrinks to 0, this will get closer and closer to the exact radius, as the distance between the line segment and the curve will be shrinking to 0. So now we're essentially done if you think about it. We have the height of our crooked cylinder, and we have its radius, if you put it on the side. Well, how do we find the area of the outer shell of this crooked cylinder? Well, if you remember, the idea is if you cut through one side of this crooked cylinder and you flatten it out, you have simply a rectangle whose length will be the circumference of the circle and whose height will be ds. So, the circumference of the circle is 2 pi times the radius, so 2 pi f of x, times the height ds. And so now, if we imagine again an infinitesimal interval between a and b, and we approximate the curve by this short line segment, the surface area of this infinitesimal shell is 2 pi f of x ds. The only problem now is we'd like this to be all a function of x. Well, if you remember, ds again is the length of this infinitesimal segment, and if you recall our discussion of arc length, we know that as a function of x, ds is the square root of 1 plus the derivative of the function squared dx. And there you go. So now you can imagine, if we want the entire surface area, and I'll call this S sub A, so the entire surface area of our surface of revolution, well, how do we obtain this? Well, we have to sum the surface area of every infinitesimal shell forming up the full surface. So we have to sum 2 pi f of x, the square root of 1 plus the derivative squared dx. But we must sum the surface area of all of our little crooked shells over the entire surface, therefore as x ranges from A to B. And that's it. So if you're given a curve y equals f of x between 2 points x equals a and b, as you revolve this curve about the x-axis, it generates a surface of revolution. And if you ask naturally, what is the area of this surface of revolution, it is obtained by evaluating this definite integral. One last comment, and that is you could have a surface of revolution obtained with x given as a function of y and revolving the curve about the y-axis. So imagine the following situation now. So you're given x as a function of y, and now you're given 2 points on the x-axis, C and D, you can imagine again if you revolve this curve about now the y-axis, this will generate another surface of revolution. And if you ask, what is the surface area of the surface of revolution? Well, it's basically the same thing now, but instead of f of x, it will be g of y. As we can see, the radius of an infinitesimal shell will be the length of this segment, and this is, of course, g of y. So, we'll integrate from c to d 2 pi times the radius, g of y, times the square root of 1 plus the derivative of g squared times, of course, dy. So it's very natural, same explanation, and here's the surface area of the surface of revolution obtained by revolving this given curve where x is a function of y between y equals c and y equals d. And that's it. So in our next video, we will consider an example of such a surface of revolution, and we'll ask, of course, to find its surface area.